All right, everybody. Well, welcome to another episode of Talking Trout. I'm Mike Coor. I'm a volunteer leader with Wisconsin Trout Unlimited. I'll be your host for the evening. This will probably be the last episode of Talking Trout that we do. We'll take a break for the summer, and we'll go ahead and we'll reload some new guests, get them lined up for the fall. We'll come back and do this again, but really excited tonight to have Nelson Ham on with us. Nelson's a geology and environmental sciences professor at St. Norbert College. He's done a lot of work studying the streams in northern Wisconsin, and he's going to kind of give us a history lesson on on how some of our trout streams just came to be. So and what we can learn from that, and how that might affect things in the future. So with that, I know Nelson, I know you spent some time in Northeast Wisconsin. You guided for tight lines, right, for a few years.
Yeah, for about 10 years. Yep.
Yeah, that's great. So, all right, again, folks, remember keep yourselves on mute, please. And then if you got questions along the way, drop them in the chat box. I will monitor that. And then with that, I'm going to turn it over to you, Nelson.
Great. Thanks, Mike. I really appreciate the opportunity to talk tonight. I've given quite a few talks over the years to some of the local TU chapters up here in Northeast Wisconsin. So Green Bay and Fox Valley and Central Wisconsin. So I'm really excited to be able to talk to a more, broader group. So the talk today, the topic I chose was actually something I talked about 2 summers ago in Kashina when the DNR had its annual trout stream restoration conference, and the focus was on Northwood's trout streams. And so we went and did a field trip, and we also had a number of talks, and I kind of gave an overview. But that talk was fairly short. It was 15, 20 minutes. And so I thought I'd expand on that quite a bit, which I hope I've done well for everybody. And the topic is how the Ice Age basically shaped Northwood's trout streams and why it matters. So why is that worth knowing? And I think it's important for a number of reasons. So the first thing we'll do is I'm gonna actually tell you what the take-home message is, so you keep that in mind. And the take-home really is that groundwater is an existential resource for Wisconsin trout streams. No matter what kind of work we do in the channel, whether it's brush bundling or other kinds of habitat work, if we don't have a cold water source, for the stream, it's not going to be a trout stream. So it really is the critical component to have the possibility of having a trout stream. So just keep that in mind. That's kind of what my focus is. I'll talk a little bit about how I got involved in trout stream geology, which is kind of a 35-year story that I'll make about 5 minutes long. Talk a little bit about the Ice Age in Wisconsin, and then focus on what I consider to be the kind of important theme. It's the connection between glacial outwash, groundwater, and trout streams in Wisconsin. And look at some examples of trout streams that I have a feeling almost everybody will know by name. So I tried to pick out some that I think are more well-known than others. And then talk a little bit about stewardship and the power of what I call in-channel restoration to support groundwater, cold groundwater, and trout streams. So this map here is one that I just got from the Wisconsin Geological Survey. It basically is just showing you all of the counties and areas in the state that have been mapped at a scale of a 1 to 100,000. There's a few exceptions to that. Starting in the 1980s as part of a coordinated program to map the Ice Age geology of the counties in the state. Now, the driftless area obviously doesn't include Ice Age deposits, but there are Ice Age deposits that go through some of them in the river valleys. There's also soils and windblown materials that got up on the bluffs, was deposited on the bluffs during the Ice Age. So there's still a lot of importance to that, and that's actually included in their program as well. Started in the 80s, they're almost done, and there will be a brand new statewide map that incorporates this 40-some years of work published sometimes this year. So how did I get involved or interested in trout streams? When I moved to Wisconsin as a graduate student in 1989, I was not a trout angler. I didn't grow up in trout country, so I was coming north. And I did a master's degree in Alaska at a modern glacier, and then had an opportunity to stay for a PhD. And the person that was advising me at the time said there might be an opportunity to work on a mapping project with the State Geological Survey if I was interested in that. And I jumped on that right away. And lo and behold, the county that I had got to map is Lincoln County, right up here, smack in the middle of the Northwoods. And I'm sure many or all of you will probably know that the Prairie River flows through Lincoln County, eastern part of the county. The little town of Gleason is there. And sure enough, when I drove up there some 33 years ago, the sign that said trout fishing capital of the world was standing outside the town of Gleason. So I obviously worked in the Prairie River area. I happened to be there the summer that the Prairie Dells Dam was removed, which was a major dam removal project on a trout stream and one of the earlier ones in the state. And so when I spent 3 years basically studying that county, I got to know the region pretty well. And I also got introduced to, the trout fishing kind of culture of Wisconsin and could already see the relationship between geology and the trout streams. And the Prairie is a really good example. Second, at the same time, my mentor was working on a project in northern Oconto County for the U.S. Forest Service. And so he invited me to kind of collaborate with him on that to see a different part of the state. And that was also really interesting for a number of different reasons. But the North Branch and South Branch of the Ocontos are in the northern part of Oconto County and come out of that in the south. And McCaslin Brook, which is another well-known trout stream and a really interesting one, is also in that county. And so all of a sudden, in a matter of about a 3-year span, I was immersed in the Northwoods as a geologist, but also getting a really quick lesson in the trout fishing history of this part of the state. The other thing I just want to point out is actually I'm really interested in the impacts of logging and lumbering on stream morphology in Wisconsin. Both of those counties have some really interesting logging stories on some of the major rivers. I'm not going to talk about that today, but that's also a fascinating part of both of those places. So what do these 1 to 100,000 maps look like? And this is the one that we published for Lincoln County. And there are, like I said, similar ones for most of the other counties of the state. You can't read all the details, but you can see the colors that are on the map. And basically, there was a color scheme chosen that would be consistent with all the maps. And even if you just know a little bit about glacial geology, anything on here that's green, either light or dark green or a shade of green, represents glacial deposits in landscapes that are mostly underlain by till, which is kind of usually this compact, very unsorted, unstratified material that's deposited directly by the glacier. And I'll show you a picture of that in a little bit. And the pink areas, which is really what we're going to focus on for the talk, are meltwater stream deposits. So those are all sand and gravel that was deposited by meltwater rivers that were flowing away from the ice when it was melting away. And just to give you a little bit of a heads up, over here in the eastern part of Lincoln County, there's the Prairie River. I can barely trace it out coming down into Merrill, and it's set right in a really large kind of corridor of what must have been some really raging meltwater rivers. And the Prairie River then established itself in those deposits once the ice had completely melted away. So what's the point is making these maps? I listed just a few things. Obviously, we want to know as a glacial geologist, what are the deposits that are there? What's the glacial history? From a resource perspective, people want to use these maps to find sand and gravel for concrete aggregate, for example, and road construction, clay, which is not that common in the Northwoods. Clay deposits are in high demand for constructing or lining landfills. They're also used to understand the groundwater supply in a region. They're used to understand which regions might be more or less susceptible to groundwater contamination. They help with landfill siting. They help with understanding and the distribution of wetlands and the type of wetlands, agricultural land management, and lots of other things. But this is just what a typical one of these maps looked like. So that was my exposure mostly to the geology of the Northwoods, and I've stayed up here ever since. And the second thing that happened to me is not too long after I finished my PhD and came to St. Norbert up here in the mid 1990s, I started to read anything that I could get my hands on about Wisconsin trout streams, and not just fishing them. I wanted to know anything that had been written about their hydrology, their geology. It didn't matter. And I came across this map, which was published in an article by C.W. Threinen and Ronald Poff. They were two hydrologists that's worked for the precursor to the DNR, and really were remarkably forward thinking in understanding where trout streams occur in Wisconsin and why. And they wrote a short article in the Wisconsin Conservation Bulletin, which is basically the precursor to the DNR magazine that many of you probably get every month. And the article was just a few pages long, and it was called "What Makes a Trout Stream?" And the opening sentence in the opening paragraph was that geologic conditions for Wisconsin's trout streams were created when the glaciers melted, and our activities determine whether they remain that way. They weren't strictly meaning all of the trout streams in the state, because obviously the driftless area trout streams are very different in their geology than the rest of the trout streams. So they were focusing mostly on this wide band of trout streams across northern Wisconsin and this very dense collection of trout streams in the Northeast. That was really what they were kind of aiming to talk about. And so when I saw this map, if you're a glacial geologist, or you're just kind of familiar with the natural history of the state, the first thing that stands out is that the pattern of some of these trout streams in terms of where they begin and end fits very closely with the Ice Age geology of the state. And I'll just show you a simple example, and we'll come back to this. The map on the right, which I'll get into more detail in a few minutes, shows you the areas that were covered by the Laurentide ice sheet during the last glaciation. So it's really about 30,000 years ago to about 15,000 years ago, but there was still an advance into the state in 10, 11, 12,000 years ago as well. But nonetheless, the white area is the area that was covered by the ice. This tan area down here into the south was area that was glaciated earlier, and then the driftless area is, of course, shown on here. If you look at the outline, the edge, for example, of the Green Bay lobe, so the tongue of ice that came down the Green Bay lowland, that basically follows the edge of the central and moving into the northeast trout streams in the state. And also, even though it's a little hard to pick out, this northern boundary as well follows roughly the edge of what was the lobes that are in the northern part, as well as the outwash deposits, the sand and gravel that was deposited in front of and beyond the ice. And like I said, almost anybody, I think, was just a real basic understanding of Wisconsin geology probably would look at that map just like I did and say, oh, well, I can actually see the outline of the last ice sheet in the state where these trout streams are located. But it gets a little more complicated and a little more interesting, I think, if you kind of look at the glacial geology in another level. And so this map on the left was published in 1975. There will be a new one published that will be very different sometime this year. But this old map is still very, very useful. And in some ways, it's more useful than the new map that's coming out. And it has to do with how they used color to make this map. The driftless area is pretty obvious, right? The light blue areas in the Fox Valley in central Wisconsin are the Glacial Lakes. There was also a glacial lake up in the Superior region. But the thing I want you to focus on is the brown colors, first of all. The brown colors, whether or not they're light brown or let's say medium brown or these dark brown areas, basically represent areas where the glacier left behind what glacial geologists would call till. And till in general is like the picture in the lower right-hand side. And of course, there's variations in what it looks like and what its texture is, but the take-home message is that till in general is usually a really unsorted, unstratified deposit, meaning it's got a wide range of grain sizes. So there'll be clay, silt, sand, and gravel all mixed together. And usually because of the finer material in it, the clay and the silt, groundwater cannot move through it very well. There is a range, and there are some exceptions to that. Some of the northern tills in Wisconsin are quite sandy and can function as aquifers, but in general, tills are less good hosts of groundwater and allowing groundwater to move through them than other kinds of deposits. So the main thing we're going to focus on today is the yellow and the orange. The yellow colors represent something like the upper right-hand picture. That is sand and gravel outwash. So that's sand and gravel that was deposited by glacial meltwater rivers that were flowing away from the edge of the glacier. It's the same for the orange areas. The difference between these two is the yellow actually is mostly beyond or in front of where the glacier stopped, and the orange, of course, is everywhere behind it. I'll show you a couple of good slides to show the difference between those two, but the main thing is that they're all outwash. So even the orange areas are much like the picture that I found that I used in the upper right-hand corner. And it's going to be the hydraulic differences, the hydrologic differences, the hydrogeology differences between these two that really play an important role in determining where many trout streams are in the Northwoods. And so I wanted to make sure I put these pictures in fairly early so you could see that. So how important is this? So the map that's on the left, well, sorry, the one that's on the right we've looked at, right, already. The one that's on the left comes from an old U.S. Geological Survey report on the major aquifers, the water-carrying or water-bearing rock units of the United States. And in the Midwest section, that sand and gravel outwash, which is obviously not bedrock, it's sitting on top of it, is referred to as the Surficial Aquifer, the sand and gravel aquifer. There are similar deposits in adjacent states, lower Michigan and Minnesota in particular. Wisconsin has these deposits fairly widespread. So this map was actually drawn in part on the map that I just showed you, which is that one. But basically all they're showing is where the sand and gravel is located. And when you see this map along with this one, I hope what's starting to stand out is even more of a correspondence between, especially, for example, the trout streams in the Northeast, some of these in the Northwest, and even some of these in the Central Sands. So I'll be happy to talk about this at the end, but obviously some of you are probably looking and going, well, why aren't there any trout streams right up here? That's one of the largest regions of the state. Remember that that's the Lake District of northern Wisconsin, very poor drainage conditions. So all that means is that instead of having nicely integrated through-flowing stream systems, we still have hundreds and hundreds of lakes. They're all still being fed by cold water as well from that surficial aquifer, but there just isn't an integrated drainage system yet of rivers. And once that becomes established thousands and thousands of years into the future, assuming that the conditions are still suitable, those will also be trout streams as well. So there's always exceptions in terms of what you're looking at, but it's the overall pattern that I wanted to pick on. So before we do anything else, I just wanted to show you so you have in mind what meltwater rivers looked like in Wisconsin, 30 to 20 to 15,000 years ago. And the picture on the left is from Iceland, if I remember right. Glaciers, by definition, when they melt and produce meltwater, they produce river systems that are totally different from anything we're used to in Wisconsin. What we're used to is single channel meandering streams for the most part. Braided rivers, which is the term that we use to describe these kind of river systems, are by definition multi-channel systems. So you have many channels that are repeatedly connecting and disconnecting and reconnecting again. It's a really dynamic environment. So the middle slide is just a vertical view on the Kinnick River, which comes from a glacier in Alaska. And I picked this out because you can clearly see the muddy water in the channels, which is that uniform gray color. And then the other light and dark colors that you see in between the channels are just sand and gravel that's sitting there that at least temporarily is not being moved by the river. And they're in the form of things that we call bars. And the thing that I just wanted you to keep in mind is just to look at some of the the bar shapes that are between the channels. For example, say this one right in the middle. In general, the areas between the river channels are kind of lens shaped. And so the sand and gravel bars are lens shaped. And I just wanted you to see that pattern, keep it in the back of your mind, because I'm going to show you a couple of slides where hopefully you'll see that same pattern and say, okay, I see the comparison between the modern and the ancient. And lastly, just like I showed before, when you have river systems like this, they're overloaded, as we often say, with sand and gravel. There's still silt and clay there too, but they're predominantly moving sand and gravel. So this is the outwash that's left behind. That's the actual deposit that's left behind once these rivers have disappeared. That's what's going to remain in the landscape. It's going to be underlain by sand and gravel. Groundwater moves through it very easily. It infiltrates into it very easily as well. And that's really what we're focusing on when looking at trout streams in parts of northern Wisconsin. So why is the outwash so good for a trout stream? I think of three things. One is that it's going to be the source of cold water. There is no other source of cold water for trout streams than groundwater. And in outwash, it's especially good because not only do you have cold water, but you also have a really good connection between the aquifer and the stream. And so in Wisconsin, like many streams elsewhere around the world, but not all of them, we have what are called gaining streams. And all that means is that as you go downstream in the channel, the discharge or the flow will increase, even if there isn't a tributary connecting to that river. The rivers will automatically be getting larger and have a higher flow in the downflow direction, even if you don't have any tributaries. The reason for that is because the groundwater is constantly moving into the channel. It seeps in along the channel sides, the walls, and the banks. If there's a distinct spot like a spring, obviously that's a place where it's coming in as well. But even if you don't have any springs at all, in a gaining stream, groundwater is always moving into the channel to maintain base flow. And like I said, the river keeps getting larger and larger and larger in the downstream direction. So we'll talk briefly about why groundwater is cold, because sometimes I've run across people and students, when I teach, who really don't know this. Why is it that its groundwater is cold, at least in the upper few tens of feet of the Earth's surface? The second thing is this base flow component. The base flow of a river plus the storm flow in a river is the total flow or the total discharge. Base flow is critical for trout streams because basically it's what maintains water in the channel, even if it hasn't rained for 2 or 3 weeks at a time. Base flow is entirely groundwater flow. Storm flow is going to be the water that, let's say, falls on the ground during a heavy thunderstorm in the summer and then almost immediately washes into the channel. Or sometimes it'll actually move laterally in the very shallow part of the ground called even the unsaturated zone. That's a special kind of flow that you see sometimes during storms. But the critical thing about the outwash is it maintains high base flow. And that's really critical in periods of drought, or at least, temporary short-term drought where we haven't had precipitation for a while. And then the obvious last thing is, and from those slides, hopefully that I showed you, it convinced you that that's the source of spawning gravel. So you've got this great three combination that makes trout streams that have these conditions, trout streams. Cold water, maintaining high base flow, especially during dry periods, and then you also have the spawning gravel. So just a couple of quick slides, because I think people are always kind of fascinated by this as to why the temperature of groundwater is cold. And usually we're talking about groundwater, let's say 20, 30, 40, or 50 feet below the surface. And this weird looking diagram is showing you temperature. It's an idealized diagram in the ground. They call it soil temperature here. And these are depths below the ground surface. So we've got 5 meters below, 10 meters, 15 is about a little over 50 feet. The thing to notice here is in an idealized situation, what happens is at the surface of the earth, right, if it gets hot in the summer, The surface of the ground feels that. Once it gets colder in the winter, it feels that as well. Same thing with transitioning from spring to autumn. But once you go a few tens of feet into the ground, the simplest way to think of this is that the ground only feels one temperature, and that temperature is the average of the entire year. And I don't remember where I took this diagram, but I remember why I did. On this diagram, it's showing that the temperature in the ground at a depth of 15 meters below the surface is around 10 degrees C, which is about 50 degrees Fahrenheit. That's really close to the mean annual air temperature of Wisconsin, averaged over every day for the year. So this actually would fit with a Wisconsin climate kind of scenario. So that translates to cold water. And this is a map that is from the EPA, and it's the average temperature of shallow groundwater. And the thing to notice is that for Wisconsin, in the northern part of the state, it says 42 degrees, and then kind of middle south says 47. A little bit below that would be 52. In general, the groundwater temperatures in the state, and there have been many places where it gets measured, you're usually looking at temperatures between 40 and 50 or 45 and 55 degrees. That's the cold water input if it gets there, if it gets to the channels to make our trout streams. Groundwater is this existential resource. If we don't have cold groundwater coming into stream channels, nothing else that we do can make that stream a trout stream. And this is ultimately why groundwater is so critical to maintaining trout streams in Wisconsin. The same is true whether you're in the driftless area and you're talking about bedrock, primarily in terms of what the groundwater is moving through, or if you're talking about other parts of the state that are glaciated and it's sand and gravel. So that was temperature. Real quick, I want to show you a map that I found to be fascinating when I put it together from some USGS data years ago. It's called a base flow index map of Wisconsin. So now we have the trout streams mapped on the state. And by the way, this layer is the most recent or nearly the most recent GIS layer of trout streams designated class 1, 2, and 3 trout streams in Wisconsin from the DNR. It's not the old map from Threinen and Poff that I showed you earlier. And the color palette that's beneath it is what's called base flow index. Base flow index just means what percent of the total flow in a stream is being contributed by groundwater. And even though we don't have the best resolution on base flow index across the state, there is a really well-known relationship among some trout stream biologists and hydrologists that in general, the trout streams in Wisconsin generally occur in places where groundwater input or base flow is 50% or more of the total flow of the stream. And once you get into less than 50%, which on here is the kind of yellow to hot colors, the red colors, you tend to be devoid of trout streams. That's the case for this big region in central Wisconsin. Just to jump ahead, that's an area of older glacial deposits, glacial tills at the surface that are not very good aquifers because they're fairly fine grained. The same is true for the eastern part of the state in this central corridor going from Green Bay down to Madison. Finer grain tills, some clay glacial lake deposits, again, not particularly good surface aquifers. And then also where you start to see these hot colors come in again in the southeast and the east, it's another example where the glacial tills are really clay and silt rich, and water does not move through them very easily. They're not aquifers at all. They're considered to be what we say is a confining unit, which means it actually inhibits groundwater flow versus actually supplying it. So just to kind of reiterate, base flow is the portion of total stream flow that's contributed by groundwater. It's critical because it supports flow during dry periods and is obviously the source of cold water. And in general, in Wisconsin and in other places too around the country where people have looked at this a little more carefully, in general, we tend to find our trout streams where base flow index is at least 50% of the total flow or more. I didn't put in a picture of sand and gravel with spawning fish on it because I think intuitively everybody knew or obviously has waded in countless rivers and seen that. But obviously outwash is critical for that reason too. So I wanted to show you some examples of these situations where modern trout streams have basically been born in these old outwash deposits. And there's some very great examples from the Northwoods that I think are really familiar. I just wanted to show you a little more background about the Ice Age history of Wisconsin, and then a little bit about some of the maps we're going to look at. I'm not going to say a lot about this one, except if you've never seen a map that shows the total area that was covered by the ice sheet during the last glaciation, the Wisconsin glaciation, this is it. And in particular, if you're on the very outskirts of this big blue area, excluding this area to the west, that's the Laurentide ice sheet. The big pink areas represent the large moraines that formed around the Great Lakes states. This is basically what North America looked like 30,000 years ago to 20,000 years ago. About 10,000 years ago, ice was pretty much completely out of Wisconsin, but this darker blue area in here actually shows the size of the glacier at 10,000 years ago. It was still a very large glacier in the landscape, but it had largely left the Midwest states, even though there was still ice in the Lake Superior Basin, which you can kind of see down here in the lowermost part. Real quickly, there was another ice sheet that was separate from the Laurentide ice sheet, and that's this area in the Western Canadian Rockies, primarily, and also kind of peeking down into northern Washington and Idaho. That was a completely separate glacier, but when they were both large enough, they ran into each other. They bumped into each other here. Here's the local picture again, just as a reminder. This little map, right, is showing you again where the edge of the ice sheet is in the Great Lakes region. And this is obviously showing you the situation in Wisconsin. What I didn't mention earlier is that all of these names basically are just labels for different parts of the glacier. And the reason glacial geologists do that is because it turns out that these lobes, as we call them, weren't all advancing or retreating at exactly the same time. There was a lot of details in terms of what the glacier was doing. And in part, that's just the way that we've communicated different parts of the ice sheet in Wisconsin is by using these geographic names or lobe names. So how complicated have things gotten? So all of those 1 to 100,000 maps that I showed you in the second or third slide, all of the information that has been gleaned from mapping in detail in all of these different counties in the state have given us a really complex picture of what was going on. So for example, this map on the left, every line that you see on here that has a name associated with it is a big moraine of some sort. So those are all kinds of various ice margin positions. The map that's on the right, you'll see a lot of names in here like Copper Falls Formation, Holy Hill Formation, Kewanee Formation, and then members as part of that. Those are distinct regions where the glacial tills themselves have distinctive but uniform characteristics. So real quickly, because it's not super critical for us, but if you're in the northern part of the state in the Copper Falls Formation, almost all the tills are very sandy and they're iron rich. So they're generally red or reddish brown in color. If you're in the Holy Hill Formation area, the tills tend to be brown to yellow brown, sandy, silty tills. And again, that's a function a lot of the bedrock that the ice was going over. And then if you're in this area of the Kewanee Formation, and then way down here in the right is the Oak Creek Formation, those are very clay to silty tills, distinctly different than the Holy Hill Formation. And so again, it's just as a way that glacial geologists have organized what we've learned about the glacial geology of the state. And again, we're not going to go over this in great detail. I can always, follow up with you later if you're interested and send you references. but I just wanted you to have an idea of kind of what we know now after 40, 45 years of dozens of different geologists mapping all across the state. So let's focus on the Outwash. And we're back at this map again. The examples I'm going to show you, I picked are mostly up here, mainly because there's some streams there that I think that many of you, if not all of you, are probably familiar with, and maybe even some intimately so. The thing, though, that I'm going to show you with these examples is I'll show you a couple streams that are in these yellow areas. And remember, I said that was outwash. More specifically, it's called unpitted outwash, which means that kettles did not form in that outwash. And so the original surface that was laid down by the Braided Rivers is still really well preserved, and strikingly so when we get to a couple of these images. And then I want to show you a couple of rivers that are in the orange area, which we call pitted outwash, which basically just means that a lot of the surfaces that were created, like a fan-shaped surface, let's say, of rivers, can be partially or largely destroyed because of kettles that formed when stagnant blocks of ice were melting away. And I'll show you a couple of images so you can picture what I'm talking about. So here's the thing to think about when we're talking about areas of unpitted outwash. So this is a figure that came from a journal article written many years ago by some colleagues at the State Geological Survey. And they were basically making interpretations of the nature of the glacier, the ice sheet, when it stood at its biggest extent in Wisconsin. So, for example, here's the glacier coming in from the right. This ridge right here, that edge, basically would be the terminal moraine. So it's the moraine that's deposited at the farthest extent of the ice. And then they were trying to show what kind of landforms would form underneath the ice when the ice is at its maximum or just starting to melt away. The critical thing is that kind of the areas that I've shown in this yellow color, that's going to be all underlain by sand and gravel outwash. And it's going to be unpitted. There aren't going to be kettles in it. Back underneath the ice, say to the right of that, the different map pattern that they're using here versus this stippled pattern is just trying to emphasize that in general, many of the landforms that formed primarily when the ice was advancing are going to be largely composed of till, so that unsorted, unstratified material. So this is from a paper and a report on the Oconto County work that I did with a mentor named John Addig. And that is, we were looking at a different situation. The landscape was really hard to interpret. It took a lot of time compared to some other areas I've worked, including Lincoln County. And the reason was because if you think about like this top diagram, that the glacier, as far as it ever gets, is right here, then it's going to deposit meltwater stream sediment, braided rivers with outwash in front of it. But the glacier, the Green Bay lobe, was melting back when it was kind of dying away down slope into Green Bay and then eventually up into Canada. And so what would happen is every time, as the ice was retreating, there would be blocks of ice that would periodically separate from the glacier. And they're still sitting in the landscape. And so when you have outwash deposited in front of the glacier in those areas of ice blocks, the outwash would either completely bury them or it would surround them. And then eventually that ice would melt and you were left with a surface, a landscape that was had very high relief, lots of details to it, lots of kettles, so lots of depressions and mounds and ridges that basically were left from this melting ice. So the primary glacial landforms that were produced by the outwash were not really well preserved. But as I'll show you, you're still in those areas, you still have trout streams. So even though the landscape may be a little bit harder to decipher, it's still largely a landscape of sand and gravel, a very good aquifer, groundwater moves through it easily, it gets cold, and so it supports all these trout streams. So before we get to those examples, I asked Mike if he thought any of you had ever heard of LiDAR. And he wasn't sure. So we threw in a few slides just to kind of explain this. This has really revolutionized the ability of geologists and glacial geologists to interpret the shape of the Earth's surface. And basically, it's a technique that's been around 20 to 30 years. The entire state of Wisconsin is now covered by LiDAR-based digital elevation maps, which I'm going to show you in a few slides. But the technology is that instead of using surveying equipment on the ground or aerial photography like was used to make topo maps, you fly an airplane over the ground and then you constantly shoot a laser out of the bottom of it. It bounces off of anything that it encounters. It could be the top of a house, it could be the ground, it could be leaves and branches. And some of those shots arrive back at the airplane. And when you get these returns, the airplane knows where it is in space because of GPS. You can create images that look like these two on the right, which are called point clouds. And so literally what you're looking at, and the bottom picture is the best, is these thousands of little dots that are on here are individual places where the laser bounced off of something and made it back to the airplane. So hopefully, obviously I chose this one on purpose because obviously it's the capital in Washington, but this lower one is really the one that tells us how spectacular this has been technologically in places like northern Wisconsin. Southern Wisconsin is mostly agriculture. So when you look at aerial photography, stereo pairs, you can see the shape of the landscape pretty easily. When you're working in the Northwoods, aerial photos for a geologist aren't that helpful sometimes, frustratingly so, because of the forest that's in the way. But this is a technique that basically allowed us to see through the forest. And what I mean by that is what you can do is the companies that fly these can process these point clouds so that they erase out any points that are higher than the solid ground. So that could be the rooftops, tree branches, leaves, power lines, whatever. And then what they'll do is with the remaining dots on the ground, they'll basically merge those together and create a continuous three-dimensional surface that shows you the shape of the Earth's surface. And that's often called a bare earth DEM, meaning by bare earth, meaning it's strictly the ground. Anything that's higher than the ground is removed. And those have become wonderfully helpful. Just to show you how powerful they can be, it's a really important tool in modern archaeology. And I think is always really interesting. The image on the left is the point cloud, the raw point cloud of a rainforest in Central America, in a place where there are no roads. It's inhospitable, generally difficult to get to. And then on the right is this same region now processed to remove the vegetation. And what you're starting to see are the remains of archaeological sites. And hopefully those stand out really well. Archaeologists now are using LiDAR to great effect to find old archaeological sites like this around the world, especially in regions that are, were largely impenetrable in terms of travel and surveying. This has really revolutionized archaeological work in many places. And it's done the same for geology. So I want to show you a quick example before we look at specific river examples. This is a place that I really like because it's got a lot of cool stuff going on. This is McCaslin Brook in northern Oconto County. Lakewood is about 3 or 4 miles to the west of us, or the west of the photo. This is mostly U.S. Forest Service area. McCaslin Brook comes in from the east, and then there is an old logging dam, a very large one that is holding up the flow to create a pond. And then McCaslin Brook continues on from it. What you're looking at is, in most places, these are deciduous trees. So the leaves are off when this was taken, and the conifers are still obviously in green. Here's what that area looked like, or looks like on a topographic map. So this would have been the kind of map that we had to work with 30, 35 years ago. You can see topography. A glacial geologist For example, these areas that have the little hasher marks in them, those would be kettles of various kinds. It kind of looks like the ground is rolling, gently rolling, some places steeper than others, but that's about it. And that's what we used to do the initial mapping years ago of northern Oconto. This is what the LiDAR image looks like now. And then again, this is a digital elevation model. So it's showing you the shape of the bare earth. The colors simply represent elevations, right? The hotter colors are higher, the greens are lower. The pond shows up as this flat area. The channel kind of works its way there through that valley and then continues on here. And I just put these arrows on to remind me to point out a couple of things to you. For example, this ridge and this one is an esker. Basically what an esker is it's the ridge of sand and gravel that's left behind when a glacier had a stream, a river flowing at the bottom of it in a tunnel. So those are behind. This ridge right here is the old logging railroad grade. This ridge bumping out here and here is the logging dam that's still there. It's breached in the middle, but that's the old logging dam. The bridge that was there for the logging railroad has been removed, was removed a long time ago. These depressions that you see right here are kind of rectangular. Those are the foundation remnants of what was probably, I think it's been described to me as like a switching station and a water station for the logging railroad. And the other thing that's really striking is a lot of these surfaces that looked like they were rolling surface are actually very flat. And that in and of itself, as well as some groundwork, field work, is a really good clue that you're looking at areas of outwash. And if you just had the topo map that I was showing you before, that wouldn't be necessarily obvious from a landscape perspective. And again, so LiDAR has changed that. These are the kind of images I'm going to show you. So we're going to look at a few. I'm going to show you one down here first, so you can see the difference between what pitted and unpitted outwash looks like. And then we'll look at a few up here, going from, again, unpitted to pitted. So first one is not too far from Wautoma. I picked that on purpose because the landscape is so strikingly different. The terminal moraine of the glacier is the area I put in green. The glacier was flowing when it was advancing to the west. It never got past this edge, this line. So this is the moraine that was left behind. And you can see that there's a very smooth, but it's a sloping surface. That was an entire area of braided rivers carrying sand and gravel away from the glacier. When the ice started to waste back to the east, remember that a lot of these ice blocks got stranded away from the glacier and they would get buried or surrounded by the outwash, and then they'd melt and they'd leave behind kettles. This area right in here is mostly outwash, but the flat surface or the flat to sloping surface is really not well preserved. That's kind of what you look at when you're looking at pitted outwash versus unpit. So let's look at a couple examples. And I tried to pick some that I hope most of you would recognize. The Prairie is the one that I'm showing on the left. So this is the course of the Prairie River. There's a tributary here. This is, I think that's Big Hay Meadow Creek, which is also a tributary. And you can see it kind of winding its course. If you look at the landscape, this really different topography here is basically what was a really complicated moraine that formed in the terminal zone near the edge of the ice. But when the ice was melting, everything in front of it, this entire area, was nothing but braided rivers like those we looked at much earlier coming off the glacier in Iceland. And basically what happened after all that meltwater was gone is that the modern river basically became kind of inset and created its own new little valley and channel in those old outwash deposits. But again, the critical thing is that for miles around this river, there's nothing but sand and gravel with groundwater that's cold and has also high hydraulic conductivity, meaning the groundwater can move through it really easily to the stream. On the right is part of a region that's kind of southwest of Anago. These are the east and west branches of the Eau Claire, which are also, I think both are designated trout streams. And so you can see the west branch here and the east branch here. Remember way back, I was asking everybody to try to remember the shapes of the bars that are formed between Braided River deposits, Braided River channels at the modern glacier. And what I'm hoping stands out for you here is here's a bar, and there's a nice bar, and here's a nice bar, and all of these small little ridges and mounds that you see preserved on that surface are those original sand and gravel bars that were between meltwater channels. So here's kind of what to think about was going on, 15 or 20,000 years ago. For the Prairie River Valley, the glacier is sitting right here. Oh, and I should have mentioned that this unique kind of moraine in Lincoln County is locally known as the Underdown. I don't know if that's a more widely known thing, but that's what the locals call it. And basically, all of the arrows that I drew on here are just arrows that are showing you the general paths that the Braided Rivers took, that the Meltwater Rivers took, carrying meltwater away from the ice. And then obviously the Prairie River is now set right into that. This part of Langley County, when again you look at these bars, you can actually imagine exactly how the channels kind of wrapped around those areas when the meltwater is still there. The direction of meltwater flow was actually towards the southwest, which is a bit different than the flow in this area from the east and west branches of the Eau Claire. It's almost straight south. But again, the reason I picked these out is because I just was trying to convince everybody that a lot of our trout streams have this very important relationship between sand and gravel from braided rivers that were here 15, 20,000 years ago today. So the next two I wanted to show are streams in pitted outwash. And this is actually the McCaslin Brook again. Only I've kind of zoomed out a little bit. This was the area that we were looking at on those figures just 2 or 3 slides ago. Here's the eskers. Here's the railroad grade. You can pick it out. The pond that showed up on the other one is actually right there. But if you look out, you don't see this kind of classic pattern of being able to see these flat surfaces with the bars even preserved. You see flat surfaces, like I kind of hone in on this one here, but it's got lots of kettle depressions in it. That was also probably quite flat in here, but now the kettle depressions look like they make up maybe more than 50% of what that landscape is. So you essentially have no flatness to look at anymore. Another case would be down here, where you have fewer kettles and you can sort of make out what to me would be an outwash plain of some sort. Here, the reason I picked this one, this is the south branch of the Oconto, but kind of in the northern part of Oconto County, is kind of unique because it has also this really collapsed kettled outwash. But right smack here in the middle, you actually have really well preserved large channels. And what had happened in that case was the glacial meltwater first kind of covered the entire area with braided streams. And then as the glacier would melt away, oftentimes lakes would form in front of the ice as well. And the water from those lakes would be channelized. So it would be going in just very specific low areas, creating its own channels, and sometimes those are really well preserved. That would be the case right in here. This is what I'm looking at. So I put together a little set of diagrams just so you can kind of think, well, what does a glacial geologist imagine was going on here from glaciation and the rivers that were there at that time, meltwater rivers versus today. So here's what we see today. And then you have to imagine that these big channel in here was not there, but instead there were lots of braided rivers that were flowing across the landscape. At some point, probably a glacial lake forms or several of them form. And the water from those lakes goes into some sort of channelized flow, and that's what would have cut these big kind of channel sides. And I hope you figured out, and the reason I pointed it out here is that right in the middle, this is a very large bar that's preserved. So meltwater was going around here, meltwater was going around here, meltwater was going through here. And at one time, it was probably the case that water filled this feature all the way from this side to this side. And today, the South Branch of the Oconto is just this really tiny kind of underfit, as we sometimes call it, stream in what used to be a much bigger valley. And when geologists see that, basically the story that it's telling you and us is that there must have been a time when there was far more more water in general, so a larger river flowing in that landscape. And glacial landscapes have countless examples of these. And the large discharges were coming from the glacial rivers, and then finally, when the glacier is gone and glaciation is over, the channels that come in after that, the quote modern channels, are just going to follow the low spots in the landscape, but they're undersized relative to how much water was there when the big channels were actually cut. Almost done. The last thing I wanted to point out was, just so you would see it, this is much farther north. This is the Pine, a section of the Pine River. This is McDonald Creek is a tributary. I picked this out because this is a place where the drumlins that formed underneath the sliding glacier, and those would be underlain by till, are clearly distinct from what's left over from the outwash that would have formed in the rivers that were flowing away from the stagnant ice. But it's a landscape where you hardly see any flat surfaces preserved anymore. I do see an esker up here. That's probably a little section of one there. Here's a little bit of an upland flat surface that's preserved, and one here as well. But for the most part, there must have been a lot of ice blocks that was in between these areas that melted to the point where you see a landscape that's a little bit chaotic and a little bit harder to describe. And again, this is an example where once the ice age was over, the modern rivers as they became established, 10,000 years ago to today, basically just as water is going to do, it's going to follow the low places in the landscape. And again, it's surrounded by outwash in these cases. So lastly, and I think we're almost out of time, I just wanted to talk briefly about, why this matters from a hydrogeologic standpoint, from a trout stream standpoint. One of the things that we're, particularly tuned to, I think, as anglers nowadays and caretakers of these rivers and streams is that careful management of groundwater resources are going to be critical to trout streams in the future. It already is now. And in particular, I'm talking about with wells, withdrawal of groundwater from wells. And it doesn't matter whether it's 100 small wells for a small community or a high capacity well that's pumping water for irrigation. Management and careful kind of stewardship of groundwater resources is going to be critical to trout streams in the future. Even though we're talking about the Northwoods, there are still contamination sources. There's still agriculture. So pesticides, herbicides, poorly developed septic systems can also be a source of things like bacteria to local streams if they move through the groundwater too quickly and aren't attenuated by the soil. And then I just wanted to give, I don't know, I guess we'll call it a shout out to all of you who do this backbreaking work, for the summer months. And you think maybe, I hope I didn't give you the impression that working in the channel somehow can't make a difference in terms of the groundwater supply. And that's absolutely not true. And I'll show you one example that's just real common. So real quickly, here's what I'm talking about in terms of groundwater management. In an area that's not developed and doesn't have any wells, every student who ever takes a groundwater class learns that If you're talking about a shallow aquifer like the Outwash in Wisconsin, whenever it rains, that the rain that doesn't get evaporated back in the atmosphere, taken up by plants, will infiltrate. It goes downward beneath the high areas and it comes upward beneath the low areas where the streams are. This is a natural kind of system. Anytime we put in a well, wells, all of them, it doesn't matter whether they're big or small, although the zone of influence will change depending on they're large or small. Wells redirect groundwater around them to go into the well because it's being pumped. And in certain situations, you can get fairly significant what are called cones of depression, which is the decline in the shape of the water table around the well because of the pumping that's taking place. And it's that kind of well activity, again, in the right situations and the right amounts, that can take away groundwater that normally would go into a stream. And in some extreme cases, you can also develop situations where you're actually pulling water out of a stream into an adjacent well than the other way around. And I will say that I've seen this in a number of places in the Central Sands, which is probably, right, our most famous story of well usage that, impacted trout streams to the extent of actually drying up, completely drying up for certain periods of time, some of the trout streams in the Central Sands. And it's the proliferation of these high capacity wells for irrigation that are really critical in terms of kind of a better stewardship and management between agriculture, between regulators, between anglers, homeowners, everybody. I will say that the high capacity well situation is not just impacting southern Wisconsin. One of the largest concentrations in the northern part of the state is on the Anago Flats around Anago, in the very same deposits and water extracted from the very same deposits the trout streams are in, the East and West Branch, for example, of the Eau Claire. Many high capacity wells go to much deeper aquifers and they have a minimal impact. But if you're taking water out of that shallowest, that surface most aquifer, the sand and gravel aquifer in the state, those are the ones that have the potential to directly impact the streams and rivers that are flowing in the same deposits. Almost done. Here's the old map that I showed you at the beginning, the old USGS map of the Surficial Aquifer in Wisconsin. Even though this is an old one, it's still widely cited. It was really well done. In the late 1980s, the Wisconsin Geological Survey put together this map, mostly for educational reasons, to try to show where in the state is it likely that a shallow aquifer is more susceptible or less susceptible to contamination from the surface. And as you might expect, they used several different data sets. They used deposit type, sand and gravel versus till. How deep is the groundwater was another factor. Other kinds of things as well. And if you look at, in general, the map pattern on the left side and just compare that, for example, to this pattern here, the Central Sands stand out. This kind of corridor going north stands out. This is in their densest concentration of trout streams in the state anywhere, is in this northeastern corridor. It also sits in an area where the deposit that it flows in are the most susceptible to contamination, and the same in other areas as well. So lastly, I just want to tell you how important the in-stream work is. It's not just about improving habitat or improving fish passage, which is critical in a warming world into the future, so fish can move freely through a stream system into colder water when the lower sections are warm in the summers, and back again. There's some tremendous work being done by TU and DNR and the U.S. Forest Service and the U.S. Fish and Wildlife Service in Wisconsin to basically completely replace these old culverts that were basically inhibiting fish passage and aquatic insect passage too. This is one of these newer types that basically is modeled in size after the stream above and below it. But what I call the power of the brush bundle and the power of the culvert, I know that probably every one of you has done brush bundling, and you know why, but there's a critical thing that actually it helps groundwater. And the reason is that in the logging era, a lot of the streams in northern Wisconsin, because of log drives, were made wider and shallower than they normally would be. And that has caused siltation in many sections of streams that normally wouldn't be there, because the flow, the velocity would be higher and the discharge would be higher. And one of the really simple, right, kind of low-tech activities that many TU chapters do is brush bundling. If you're narrowing up that channel, it's going to increase the velocity, which starts to move some of that silt away. It's really effective in the right situations at getting some of that fine sediment off of that beautiful sand and gravel that was left behind by the glaciers, and also enhances groundwater input into the channel by seepage. So I never want anybody to think that the in-stream work somehow isn't also helping the groundwater situation. It absolutely does. And it's a very powerful tool, even though it seems like a relatively simple one to utilize. I'm going to stop there. Thanks for listening, and I'll be happy to try to take some questions.
That was great, Nelson. Thanks so much for putting this together and presenting it for us. I've got a couple of questions for you. Before I get to that, I'm gonna jump in, and Jim's got a question here, specifically related to the Prairie River. They put in the chat. It says recollection is that the stream bed is quite stony with some substantial sized rocks. Is that a characteristic that's fairly consistent with your description of these trout streams that are in these outwash areas?
Yeah, the prairie is really interesting. And the reason is, for those of you that have been up on the prairie, you probably know where the Prairie Dells Dam was. And the reason that dam was built there was because there's a really large outcrop or exposure of Precambrian rock. So granites, for example, and things like that. So it really depends what section of the stream that you're in, but there are sections where there's a lot of bedrock exposure, and that bedrock is contributing those really large pieces, that's kind of stony landscape. As you move upstream, for example, so you're in the area that's above where the Prairie Dells Dam was, and you're getting in the area of Gleason. That area around Gleason is a really classic example of a region where that stream is flowing almost entirely in sand and gravel. And it has these enormous, beautiful meanders to it. You can actually see many times, if you look at stream maps and you're just looking at the shape of the stream, the course that it takes. In Wisconsin, there's lots of examples where you'll see a stream. I'm trying to think of the Wolf is actually a really good one. And you can look at this afterwards. If you look at the course of the Wolf River coming through the Menominee Indian Reservation, again, that's a place where there's tremendous amounts of bedrock that's really close or at the surface. The stream has very straight sections. It has some sort of meanders. It has some really funny bends in it. When you come south of Shawano, just a couple of miles into that middle section of the Wolf, if you look at it on Google Earth Maps, and it's very clear when it happens, you're going to see these tremendous meanders develop, this meander belt. And that's again where the stream is changing from a lot of bedrock control to a lot of sediment control, sand and gravel again. So yeah, the prairie has interesting sections. And again, where the Prairie Dells Dam was built was specifically put there because there were large enough rock outcrops that it made the natural place where you could build this dam and back up the water. But like I said, in '91 was when that dam was taken out. And then there was one more dam near Merrill that was taken out. And I remember someone from DNR telling me at the time, when the second dam was taken out, the Prairie had become one of the longest free-flowing streams, and trout streams, obviously, in the state. So there was some really interesting work done there that was not very popular at the time. The people that were doing it, the DNR and so forth, who had made that decision, got a lot of flack from local folks about that. But it's an absolutely spectacular, piece of water again.
Yeah, thank you. And I will say, as somebody who's visited it years after the dams have been removed, it's a pretty spectacular sight to walk into that gorge there and just see the
Yeah.
river down below tumbling through. If you're in the area, stop by and check it out. It's well worth the visit.
Yep.
Can we talk about the LiDAR for a little bit?
Yeah, and I saw that Brian Larson said LiDAR great for effigy mounts. You're exactly right. In Wisconsin, people there's Facebook pages where people constantly share LiDAR from Wisconsin and are trying to find effigy mounds. And of course, the concern is that some people might find some and they're kind of more nefarious and actually want to go in and try to collect if there's artifacts there. But it's become a really powerful tool for effigy mound work in Wisconsin. The thing that I should point out is LiDAR in the Northwoods, the quality of the digital elevation model you get in northern Wisconsin is going to be different from southern Wisconsin in agriculture. And the reason is, when you're flying over a farm field, every single laser point that you shoot down, most of them are coming back to the airplane. So you get a very dense cluster of points. Just every few feet is the spacing usually between the points for most modern surveys, although you can do that at a much higher resolution. When you're flying over forested regions, there's only going to be a certain percentage of the laser shots that are going to somehow make it through those branches, bounce off the ground, and make it all the way back up to the airplane. So even though it's still this spectacular amount of information that you start to be able to look at, it's still one of these situations where it's not the same as if you were flying over basically an area that was unforced. If that kind of helps put it in perspective. One other thing I should say is, if you're interested in looking at LiDAR, it's now available for the entire state, and you've probably already used it or seen it. For example, the DNR's, what's it called? Trout Regulation and Opportunity User Tool.
Yep.
That has the LiDAR as the base map when you're looking at it. The surface water viewer from DNR, I believe, has that base map on it as well. But those are the two probably easiest, places to access it fairly quickly. And like I said, you've seen it, even though you may not have known that's what it was.
Yeah. And that was actually one of my questions are the maps publicly available? Because you mentioned a lot of times if I was wondering who's actually flying the airplane or who's gathering the data.
Yeah.
If it's a private company, maybe they want to
Great question.
sell that, or if it's a government agency, they'd probably be more apt to make it available to researchers. And
there were limited LiDAR data sets available 15, 20 years ago. And in general, all of those were paid for by funds that were either private or even county funded. So for example, Oconto County had LiDAR before many other counties did in the state. But especially as a result in the last 20, 25 years of fairly extreme flooding in different parts, right, of the state decided kind of collaboratively with the counties to get money to basically map all the counties in the state. And the real reason they did that was not because of looking at cool glacial geology landforms. It was to make better floodplain maps. So the topo map is only so good if you're drawing on there, what you think is the limit of the 100-year floodplain. The LiDAR takes that at a completely different level. And so the reason that many counties got the money to do that was because of this urgent need for updating and having better, more accurate floodplain maps. The money for most projects then started coming from the federal government, and the federal government stipulated that they could not sell that data. It had to be a condition for getting the grant to get the data was that you had to make it publicly available. So it's available now for the entire state, freely available. I think the last county that did not have it was the Menominee Indian Reservation, because the first round was actually paid by them, but now they have gotten a new modern survey that was funded again by the U.S. Geological Survey, so that's publicly available too. I actually have a really good GIS person that teaches in our department part-time from Brown County, land information officer, and he's actually put together a website. It's an app that has all of that LiDAR on there, plus a lot of geology layers, plus I had him put on there the trout stream layers as well. And if people are interested in that, they can email me and I can send them the link. But I'm just telling you that like the Trout, that opportunity user tool is now utilizing that as well.
That's great. Yeah, I think maybe I shouldn't say this because this is going to go on YouTube and out into the internet world. I should check my notes first. But I feel like I've had conversations with folks at, like, say, the Wisconsin Wetlands Association that were interested in using LiDAR to more accurately map like wetlands on the landscape and things like that. It just feels like it opens up. There's a lot of possibilities there, and we're probably just scratching the surface of the uses of these
Yeah,
the new age of topographical maps.
Yeah, and just to give you a perspective, the old topo maps, which probably everyone has used at some point, but many people never knew that the accuracy of those, vertically. So let's say you think you're on a topo line that says you're 1,500 feet above sea level. That could be off by several feet. And the location of the contour could be off by several feet as well. The LiDAR that's generally available for the state now, and then utilizing GPS, the vertical accuracy is usually within a few inches. It's less than a foot, well less than a foot. And then with GPS, of course, you can find your position very accurately. So this really wasn't just like a little step forward. It really was a transformative thing for all kinds of uses: surveying, floodplain mapping, construction. Road construction utilizes LiDAR-based maps as well, integrated into GIS. And again, for geologists interested in the landscape, this was really a revolution.
Yeah. So I know we're kind of running out of time, but I was hoping you'd maybe just take a couple of minutes. I want to go back and talk on this. The 50% is kind of the magic number for like the percent of base flow in a stream that's coming from groundwater, right? Like if you've got more than 50% of your base flow coming from groundwater, there's a really good chance that that's a trout stream, right? Or has the potential
it has the potential to be one, absolutely, because the groundwater in everywhere in the state is cold enough to support a trout stream. And actually it's cold enough even if you go south of Wisconsin, in across the middle part of the country. So it sets up the possibility, but there's always going to be local things that can influence whether that's really going to work or not. But right, we all know that you have to have cold water first, and the more cold water, the steadier the cold water you have, the better. So the other thing that happens when you have high base flow streams is they show, even though they're cold, but they also, the high base flow moderates the temperature extremes between summer and winter. And as I always remembered it, unless something's changed in trout stream biology, trout did not handle obviously really hot weather very well, and nor is really, really cold weather great either. And so when you have a spring fed, for example, like in the driftless area, it's kind of ideal. When you have these springs that are, attributing a significant amount of cold base flow, even when it's really cold outside and you've got ice and snow in the landscape, the streams are still open. I mean, that's one one thing that can be the product of that. But the flip side is in the summertime, where we're starting to get these really hot spells. Obviously, that's really important as well, keeping them cool enough that trout that so the temperature isn't lethal to them. The one other thing that I put a couple extra slides in just to remind me, but the one other thing that I just wanted to point out is there's a lot of conversation right now about the future changes in climate of Wisconsin, obviously, and the predictions are of wetter and warmer conditions. The problem there is that it's really difficult for a hydrologic modeler to try to forecast exactly how the warmth and the wetness, the higher precipitation is going to influence stream temperatures. And the real problem is, and this isn't me, I rely on a woman who I've known for 30 years, who's the USGS, essentially the state hydrologist, Faith Fitzpatrick, who's really knows more about Wisconsin rivers than anybody. The issue is that we're starting to see precipitation that's in extremes. So all of a sudden you get 10 inches of rain and then there's 3 weeks of nothing. So we're starting to see these really extreme events with these really powerful cold fronts. The kind of traditional warm front system where, the rain falls at a moderate rate for 2 to 3 days, spreading out the water enhances infiltration and contributes to groundwater flow. If you get a ton of rain all at once, oftentimes a lot of that rainfall begins to flow overland directly into the streams as storm flow, never made it into the ground and to become part of the groundwater system and cool. That's really a tough thing to assess, for the people that are trying to forecast exactly what's going to happen. So I've seen examples of even the DNR, for example. It said, well, if it's going to be wetter, then things might not get as warm in these streams as we forecast without it being wetter. But the problem again is that you don't know how much of that rain is going to be coming down in a way that will infiltrate into the aquifers versus come down in kind of extreme storms that's going to run off real quickly. And I think that's one of the big kind of question marks. If any of you have seen some of that work or heard about it, it's a very tough thing to try to figure out right now.
Yeah, that's interesting. So thinking about that, let's take it to the next level, right? So you've got a marginal trout stream and maybe let's say like the groundwater base flows at, right around 50%, or maybe it's even a little less, because let's say we get more and more of these big runoff rains, and that's more percentage of the water starts coming from the runoff that as opposed to the base water. Is it possible to change that like on a landscape level? Like, would we be able to, as humans, like go in and change things on the landscape enough to like flip that percentage a significant amount? Or is it already kind of predetermined by how these stream channels have already, like how the landscape has already formed over the last, since the last glaciers?
There's a number of studies, including dissertations and master's thesis at Madison and some of the other schools that had looked at, for example, there's a really interesting, was done in the 70s or 80s, master's thesis that looked specifically at how land use change in the Prairie River Valley might have affected stream flow. And the interesting thing is it wasn't, or I should back up. The reason they chose the Prairie River is because the Prairie has one of the longest stream gauging records of any stream in Wisconsin. So there are a number of rivers, many of them were used as log driving rivers. So they were gauged fairly early. So they're 100-plus-year-old records, compared to most streams in the state where you might have 10, 20, or 30 years of record. Or you might have 10, 20, or 30 years record and it's not being gauged anymore because of USGS funding. The other one that I know about is the South Branch of the Oconto, I think it was too, had a similar study done. And that was trying to look basically at, for example, when you went from forest to cutover to modern forest, do you see obvious things in terms of stream flow that are reflected in these land use changes? And again, like I said, the Prairie River had a similar one. and it's complicated again. One of the problems is, for example, if you have fairly dense forest, that can intercept a lot of precipitation and decrease infiltration rates depending on the particular kind of species and trees you have in the cover. Even though you might think that you want those trees there versus, what it was like before. In the Oconto Basin, it's so sandy in some of the regions they were looking at that even though you went from forest to cutover and slash everywhere, you didn't see more runoff that caused more storm flow that caused larger floods, for example. And the idea there was that no matter what the situation was, because the glacial geology is so gravelly and sandy that all the way up to the surface, that any rainfall that falls almost never channelizes its overland flow or storm flow. It almost all infiltrates, even if you've got really high precipitation events. And I think what's happening now is some of the people at the U.S. Geological Survey are starting to use more sophisticated techniques to go back and look at those records again. That wasn't really available to some of the folks looking at this 40 or 30 years ago. The example I can give you real quick is when I moved to Northeast Wisconsin and I started to trout fish, and I actually got the bug when I worked in Lincoln County. So about 35 years ago, I was trying to fish closer to home. And I knew in short order that if it was really raining like hell for a couple of days, that certain streams that I might drive to would be high and muddy and difficult to wade in. But like the south branch of the Oconto has a section that flows through an area of sand dunes and sand and gravel outwash, and you would have a little bit of off-color water. It wasn't particularly high or blown out. Obviously, the discharge went up. And it was really just a function of the geology and whether or not you had till in the watershed that enhanced the overland flow and reduced infiltration versus being in a sandy, gravelly watershed where more of the water quickly could infiltrate into the ground as groundwater and get cold, versus flowing overland. So it's a complicated world. It's not something that I'm an expert at, but I have talked to the people that basically are. One of the big concerns to the hydrologist for the USGS for the state of Wisconsin is, she said, one time I was at a conference with her and we helped run a field trip and we were talking and she said, I'm actually not that worried about more rain. She said, I'm worried about droughts. That what's going to happen if the nature of precipitation changes to these extreme rainfall events and then separated by multiple weeks of very dry conditions versus kind of a more stable, constant or nearly constant, passage of fronts with moderate rainfall. That's a legitimate concern for some of the hydrologists in the state thinking about the coming few decades.
Yeah, we've heard certainly. I think I remember conversations with folks on the fisheries side of things too, looking at that, and that was their big concern, was that's when we're going to see the stress on the fish and the populations dive is when we get those prolonged drought conditions, and they're coming. It's just a matter of when they're gonna hit, how bad, how severe. So,
and if folks didn't know, but with this drought situation is it's really well documented by some older articles. UW-Madison, I think, used to have an agriculture journalism program way back. And they would basically did a great job documenting photography and articles, agriculture in the state of Wisconsin. In the 1930s, during the Dust Bowl, the central sands of Wisconsin basically turned into a dust bowl. Would have reminded you of a picture from Kansas. And there are photographs of 3, 4, 5 foot tall sand dunes marching across the landscape in Oconto County, up here where I'm at. So even though most people think of the Dust Bowl being a Great Plains thing, it had a very measurable impact on Wisconsin, including in areas of trout streams. And that's kind of the extended drought situation where then stream levels obviously can drop so low that, you know, you actually abandon and dry up some stream channels. And that was the case in central Wisconsin during the Dust Bowl.
Yeah. Well, it's 9:30, and I guess I want to. I think we should probably leave it there. I know we didn't get time for you to list off all of your favorite brook trout streams in the Northwoods, so we're going to have you back on to have that conversation at a different time. But I really appreciate you coming on and talking about this and sharing your knowledge with us.
If anybody has any questions, please reach out to me. I'm easy to find on the internet. If you just type my name in and St. Norbert College, you know, my email address will pop up. I'm happy to communicate, talk with anybody. And I actually want to know where those trout streams are because I haven't gotten to fish nearly as much as I wanted the last few years, but I've been slowly going back to some of these places.
Yeah. All right. Well, thanks again. And everybody who stuck around, be well this summer. If you have ideas for future episodes of Talking Trout, guests or topics you'd like us to cover, by all means, shoot me an email, give me suggestions. So we're going to kind of think about it over the summer and start lining up the fall guests. So be well, and we'll see everybody on the stream this summer. All right. Take care.